The last thing to talk about is this idea of the properties of the transversals when we're talking about parallel lines. So if you've got 3 or more parallel lines for that matter, and you have a transversal that cuts it, so there's one, but then you have another transversal. It does not matter where I draw the transversal, it's always going to cut the parallel lines in the same ratio. It doesn't matter. So I mean there's a third one. So what we know is all those ratios, AB to BC, PQ to QR, XY to YZ, is going to be the same ratio. That's just the ratio of intercepts of parallel lines. Now I haven't bothered to prove it there, but what you're basically doing is saving time on proving similar triangles. Could you imagine those transversals, assuming they're not parallel of course, if you were to keep drawing them at some point they'd meet. And what you're basically doing then is creating similar triangles. And then you could use the similar triangles to prove those ratios were equal. So it's to save a bit of time there, you don't have to worry about the similar triangles. So in fact, if you actually have a similar triangle question, where you have 2 parallel lines already drawn in, what you can do to save proving the similar triangles is you can, well, construct a third parallel line going through the vertex, and then you can use the ratio of intercepts of parallel lines rather than having to prove the similar triangles. Okay? So it's a little bit of a shortcut if you've got that situation. Okay, so let's put some numbers in it. So for instance, if I wanted to find x, it's just a matter of substituting into the ratio then, and away we go. There we go, x equals 9. And so that ends our look at Euclidean geometry. Okay.